and then hold it there for a while. Now, how long do you have to hold it? That depends on the thickness of the metal. Okay, when a heat treater does this, they look at the thickness of the metal. The thicker it is, the longer you got to hold it there to, let it heat through. Always the surface will heat up real fast, but the inner part takes a little bit longer, right? And then you have to cool it down slowly, okay? The difference is, for example, like a normalizing, which is another heat treatment, and annealing, you let it cool down in a furnace very slowly, controlled cool, okay? Normalizing, you do what they call an air cool. You take it out of the furnace and then let it cool down. It goes a little bit faster. Then the results are not as good, but it's a lot cheaper than having to leave it in the furnace. And then here you see process anneal. You know, process anneal, they don't even have to heat it up to really high temperatures. That's kind of like a recrystallization process where new little grains start to grow, and you relieve stresses, basically. That's what they do in there. Spheroidizing anneals, they're used for like high carbon steels, and it's basically when you have a high carbon steels, you had a lot of that cementite in there, right? And you want that cementite dissolve out of that microstructure so it won't be on the grain boundaries and give that brittleness, so you want to restore some of the ductility. Okay. Then here you see actually a diagram. They call this the TTT diagram, time temperature transformation diagrams. This is for strengthening heat treatments they use this. Remember, for the strengthening heat treatments, what was the difference between a strengthening heat treatment and a processing heat treatment?
How it was cooled.
What's that?
How it was cooled.
Yes, how it was cooled, exactly. The processing heat treatments, you cool them slowly. You can pretty much predict the microstructure that you're going to get by using the equilibrium diagram. Well, for the strengthening heat treatments, where your purpose is to make a material a weak material, make it into a strong, hard material, okay, if that's your goal, then you cannot use the results of the phase diagram, the microstructures that you would expect. You cannot use it. And you have to use other types of tools. Now, you can still tell, for example, here he's using a eutectoid steel, right? This is a TTT diagram, time temperature transformation diagram for eutectoid steel. So that tells me a eutectoid steel that has 0.77% carbon in there. Remember I mentioned that earlier, right? So, because for every steel that will have different TTT diagram, and the reason they call it time temperature transformation diagram, right? You have an axis here, time in seconds. This is on a logarithmic scale because they can't get all the data on there if you had a linear scale. And then here is the temperature here, right? And then you can see the transformations occurring. These are pictures here, microstructure pictures. You can pretty much predict the microstructure that you're going to get by using the equilibrium diagram. Well, for the strengthening heat treatments, where your purpose is to make a material a weak material, make it into a strong, hard material, okay, if that's your goal, then you cannot use the results of the phase diagram, the microstructures that you would expect. You cannot use it. And you have to use other types of tools. Now, you can still tell, for example, here he's using a eutectoid steel, right? This is a TTT diagram, time temperature transformation diagram for eutectoid steel. So that tells me a eutectoid steel that has 0.77% carbon in there. Remember I mentioned that earlier, right? So, because for every steel that will have different TTT diagram, and the reason they call it time temperature transformation diagram, right? You have an axis here, time in seconds. This is on a logarithmic scale because they can't get all the data on there if you had a linear scale. And then here is the temperature here, right? And then you can see the transformations occurring. These are pictures here, microstructure pictures that they took with a microscope. And this first line here, this line here, they call that the start of transformation. And the second line here is the end of the transformation. So in order to make a tempered steel, okay, well, the first thing we had to do was heat it up to high temperatures, that's what I said, right? And then cool it very rapidly. But then you got that martensite, that very unstable structure, right? And then we have to temper it, we have to reheat it. Well, first we have to make martensite. So what we do at time 0, okay, we heat it up above this line here, And we get into what they call that austenite stable region. Remember the austenite that I talked about earlier? Right, got a few slides back. There was the austenite region, so we gotta heat it up into this region. If you have a detector at steel, you gotta get it above this temperature. So let's say you hold it, get it there, soak it real good, and then, you know, you have that stable austenite, and now we've got to quench it. We've got to cool it down very rapidly. Now the heat treater has many.
Sorry that I interrupt. Yeah.
Oh, we have a few more minutes.
We are. Can you show the
Yes.
students the sparks?
Yes,
Yeah.
Okay, all right, sure.
Sorry.
That's all right. Here is, as a matter of fact, next slide.
Oh.
Here, this is what we did last year. We have here the grinding wheel, and Tyler Dahlke, he designed and built a fixture together with Mr. Weller, but he did pretty much all the work. Okay? And here you see a metal specimen that is held against the grinding wheel, and here's the sparks that are created. Okay, and we like this method because it's a safe method to use. Okay, and that we can actually do in a laboratory. And here the spark pattern is created, and you see he took on this metal specimen, he took Rockwell hardness reading, Burnell hardness reading, and then he used a software. Image J, thank you. We have it on our computer. Image J, and he took pictures of this, and he measured the spark length and the angle in between here, and I think he even measured the angle, horizontal angle. Now, there's a certain judgmental factor occurring, right? You see these weird sparks going here, so that's why. That's one of the reasons where error comes when people try to do this again. Okay, there's any science is usually not exactly 100% correct, or maybe correct, applicable. Here you see the spark pattern that he created. He actually put a little white card there and let it spark for 30 seconds. And you see the spark pattern. Well, different materials give different spark patterns, and that was pretty much what he did. Now, Mr. Goody, what he's going to use is a thermal imaging camera here. You know, that's actually from the geology department. So Dr. Dodge,
Dr.
yes,
Dodge.
Dr. Dodge, yes. And she helped us out with this, and actually we have this one now in my office, right? And we need to look at this and try it out and all that. But here, you know, we want to do the same type of thing, so we're going to make Mr. Goody do the Burnell hardness testing, tensile testing, but also use a thermal imaging camera and look at the increase in temperature. Now, all the specimens got to start out basically with the same ambient temperature, which won't be a big problem. And and then we heat up a metal specimen, right, plate there, see what the temperature increase is, and see if we can distinguish between that. And that's pretty much it.
Oops.
I think that was the last slide. Let me see. I might have one more. That is the grinding.
Questions?
I actually have one. I'm not an engineer, but I'm also in the geology department. Is it possible to actually tell the origin of where your steels come from?
Where the origin?
The origin. Or is that a little bit harder? That kind of gets more into the geology.
I would not know that. I mean, we have a hard enough time, honestly.
Well, I know that originally, most of the steel was made here in the U.S., so it was actually mined here in the U.S. But
Right.
you get a lot of stuff that comes in out of China and other countries, and I was wondering about
Well,
if that affects their strength.
well, that's an interesting question. I know that Mr. Weller, he ordered steels for us, okay? And he can buy steels that they say it's in there, and some steels, they have a definitely recorded history on them. So if it's really important, we get the history on it, and we can see where it came from. But no, you cannot tell, you know what I'm saying, that I know of. We just have to have the history, but it becomes a lot more expensive to get those steels.
Yeah.
And we have talked about that before, that,
So it's almost like pedigree seals.
Well, I mean, it's kind of like a lot of things. It's like honey, you know, a lot of stuff they'll come in out of China, but it's not actually honey. It's been watered down with corn syrup and stuff.
Yeah,
And so it's just something that you kind of think of, you know, way to cut money, cut corners.
You don't know sometimes, and you know,
That's where I guess this would
Yeah.
come in handy. Is,
Yeah.
You know that it's actually what it's supposed to be.
it will help, you know, determining what type of steel it is. But I couldn't tell where it came from. But it will help. You know, doesn't have that strength property, doesn't have that hardness that we know what it is. And then by looking at these spark patterns or maybe the thermal imaging cameras, we can see he's going to hopefully create a little library, and only of a few materials. We're only going to do like 10 of them or so. And then we're going to have unknown specimens there, and then we're going to have a group of students run through there and have them do it, and then see a comparative analysis, see how well the results come with what he had set from his little library. But we took about the most 10 common most steels that people around here use. Okay, because we can't do thousands of steels, you know, like the people did in the '60s. They have a book, and there's probably, I'm not kidding, about 1,000
My
pictures in
grandfather
there.
worked in the steel
So-
mills up in Pennsylvania, so that's why I was kind of
Oh,
curious.
yeah.
So what is the difference then to the atlas that was created in the 60s and what you are trying to do?
That's a big difference. The atlas that was created in the '60s, really what they did, the only thing they did, which was amazing, was they took pictures of all these different types of steels, and they looked at it and say, okay, there you can see the silicon burst occurring and all that. So they have thousands of pictures. Now, one thing that Tyler Dalkey did different, he said, you know, this is going to take too long, you know, to go through this, and really it's already been done. And he came up with, why don't we start looking at taking pictures, looking at image J, and looking at the spark length, looking at the angle, and now we want to try to do using the thermal imaging camera, which they didn't do in the '60s. You know,
So it's an advance in the technology that we have now can advance.
yeah, we have
the-
better
the-
equipment and all that stuff.
yeah.
Now, I don't know, quite honest with you, if we're going to get good results. That's what I really don't know.
Right,
That.
yeah.
That's what is going to be your research and trial and error, and hopefully we get good results. I
Yeah.
cannot promise that. I mean,
Well, any results is good.
Yeah,
You know,
yeah.
if you can do it or you can't, you
Right.
have an answer.
right,
Right.
you know, and so I actually want to meet with Mr. Goody in a while in the office. I gave him already material. Right, and,
To read, yeah.
Yeah.
You gave it to me too.
yeah.
Well, excellent. Well, I am sure you are in a hurry to go to next class. All right. So
We're all jumping up.